Welcome back. In this video, we're going to look at examples of finding area of surfaces of revolution with parametric equations. Let's get to it. All right, so here's our first example. We want to find the area of the surface formed by revolving the curve represented by the parametric equations around the x-axis. In this case, we have x equals 3t and y equals t plus 2 for our parametric equations. And we're just going to be looking at the part of the curve represented by these equations from t equals 0 to t equals 4. That's the part of the curve that we will be revolving around the x-axis to form a surface of revolution. All right, and in order to calculate the area of that surface of revolution, we need to know the proper formula. In this case, since we are working with parametric equations and we are revolving around the x-axis, our formula will look like this. The area of the surface of revolution S is equal to 2 pi times the integral from t sub 1 to t sub 2, which are two values of t for our curve, of g of t times the square root of dx dt squared plus dy dt squared. Now g of t corresponds to what y is equal to from your parametric equations, right? In general, for a set of parametric equations, we say that x is equal to f of t and y is equal to g of t. Right, x and y are just equal to some function in terms of t, and for x we say it's f of t, and for y we say it's g of t. So whatever y is equal to, which in this case is t plus 2, that is going to be g of t in this formula. And that part of the formula is the only part that's going to change when we look at an example where we are revolving around the y-axis instead of the x-axis. All right, when you're revolving around the y-axis, instead of having g of t, we're going to have f of t. But we'll take a look at that in our next example. For now, let's just focus on revolving around the x-axis. And so we're going to use g of t in our integral. And then it's multiplied by the square root of dx dt squared plus dy dt squared. Dx dt is the derivative of our parametric equation for x with respect to t. And dy dt is the derivative of our equation for y from our parametric equations. And so we'll take the derivative of x and y with respect to t and use those to help us set up this integral to calculate the area of our surface of revolution. All right, so far we know this. We know that g of t is equal to t plus 2. That's just what y is equal to. And now let's find dx dt and dy dt. dx dt is equal to the derivative of 3t, and that's just going to be 3, right? The derivative of t to the first power will just be equal to its coefficient, which is 3. And then dy dt, that will be equal to the derivative of t plus 2. And a derivative of t to the first power is just going to be its coefficient, which in this case is 1. So we have 1, and then the derivative of 2 is 0 because 2 is a constant, and the derivative of all constants is 0. All right, so dx dt is 3 and dy dt is 1. Now we can plug these values into this formula, as well as g of t, which is t plus 2, and we will be able to set up an integral that will represent the area of the surface of revolution in this example. So we will have that s is equal to 2 pi times the integral from t sub 1 to t sub 2, which in this case the values of t that we want to integrate between will be from 0 to 4. So we'll have 0 to 4 as our bounds of integration. And then inside the integral, we'll have g of t, which is t plus 2. So we'll have t plus 2 times the square root of dx dt squared plus dy dt squared. So we'll have 3 squared plus 1 squared. All right, so we'll have 3 squared plus 1 squared. And then don't forget dt. Okay, so now we have set up our integral that will calculate the area of the surface of revolution. Now all we have to do is simplify the integral and then solve it. And so the first thing that we can do to simplify this integral is square 3 and square 1. 3 squared is 9 and 1 squared is 1. So this will be equal to 2 pi times the integral from 0 to 4 of t plus 2 times the square root of 9 plus 1. And then we'll multiply by dt. All right, but 9 plus 1 is 10, so we have the square root of 10 right here, and that would just be a constant, so we can pull the square root of 10 to the outside of our integral, and this will be equal to 2 pi times the square root of 10 times the integral from 0 to 4 of t plus 2 dt. All right, so that whole square root part was just a constant. We had the square root of 10, so we brought it to the outside of the integral, And now we just have 2 pi times the square root of 10 times the integral from 0 to 4 of t plus 2 dt. And we know how to integrate t plus 2. This is a pretty simple integral that we can solve. We can use some very basic integration rules to integrate t and 2. And so if we do that, this will be equal to 2 pi times the square root of 10 times the integral of t, which if we use the power rule for integration, we'll add 1 to the exponent and then divide by that new exponent. And so we have t to the first power, so 1 plus 1 will be 2. So we'll have t squared, and then we need to divide by that new exponent of 2. And then we'll add that to the integral of 2, and 2 is a constant, and the integral of a constant will just be equal to that constant times the variable of integration, which in this case is t, so the integral is 2t. All right, and then those terms are evaluated from 0 to 4. And now what we have to do to calculate our area is evaluate this expression at 4 and subtract the evaluation at 0. But notice that when you plug 0 into each of these terms, it's just going to be 0, right? 0 squared is 0, divided by 2 is still 0. And then you're adding that to 2 times 0, which is also 0. So we have 0 plus 0. So we're really just going to be subtracting 0 when we evaluate this at 0. All right, so just keep that in mind. What we're going to have here is that this is equal to 2 pi times the square root of 10 times these terms evaluated at 4. So we'll have 4 squared divided by 2 plus 2 times 4. And then we're going to subtract evaluating these terms at 0, which like we discussed is 0. Okay, so now if we simplify, I'll continue our work up here. This will be equal to 2 pi times the square root of 10 times 4 squared divided by 2. 4 squared is 16. So we have 16 divided by 2, which will be 8. So we have 8 plus 2 times 4, which is also 8. So we have 8 plus 8, and that's 16. So this is equal to 2 pi times the square root of 10 times 16. And 16 times 2 is 32. So this is equal to 32 pi times the square root of 10. That right there is the area of the surface of revolution formed by revolving the curve represented by these parametric equations between these two values of t around the x-axis. All right, and so that is it for this example. Now let's look at another example, except instead of revolving around the x-axis, we will revolve around the y-axis. All right, so here's our next example. We want to find the area of the surface formed by revolving the curve represented by the parametric equations around the y-axis. In this case, we have x equals 1/3 t cubed and y equals t plus 1. And we're just going to be looking at the section of the curve represented by these equations from t equals 1 to t equals 2. That is the section of the curve that we are revolving around the y-axis to form a surface of revolution. All right, now if you want to calculate the area of a surface of revolution formed by revolving a curve around the y-axis, you need to use a slightly different formula than what you use when revolving around the x-axis. In this case, the area of the surface will be equal to 2 pi times the integral from t sub 1 to t sub 2 of f of t times the square root of dx dt squared plus dy dt squared. All right, and then don't forget about dt. So this is the exact same formula from before, except instead of g of t inside our integral, we have f of t. So instead of using what y is equal to in terms of t, we're going to be replacing that with what x is equal to, because f of t corresponds to the function in terms of t that represents x from your parametric equations. So in this case, f of t is equal to 1/3 times t cubed. Okay? So keep that in mind. We're going to use that when we set up this integral. But before we can completely set it up, we also need to find dx dt and dy dt, which are the derivatives of x and y with respect to t, respectively. So let's start with dx dt. The derivative of x with respect to t will be equal to the derivative of 1/3 t cubed. Now we can use the power rule for derivatives here. We'll multiply this exponent down and subtract 1 from the exponent. So we'll have 1/3 times 3 times t squared. All right, 3 multiplied down, we have 1/3 times 3, which will actually become 1, right? 1/3 times 3 will just be 1. These 3's will cancel out. And because of this cancellation, dx dt is just equal to t squared. All right, now for dy dt, that's the derivative of y with respect to t. That will be equal to the derivative of t plus 1. And the derivative of t is 1. right? The derivative of t to the first power will just be equal to its coefficient, which would be 1. We just have 1t. And so we have 1 plus the derivative of 1, but 1 is a constant, and so the derivative is 0. So dy dt is just 1. All right, so now we have f of t, dx dt, and dy dt. Now we can substitute them into this formula, as well as our bounds of integration for t, to set up an integral that will allow us to calculate the area of this surface of revolution. So we will have that s is equal to 2 pi times the integral from t sub 1 to t sub 2, which in this case will be from 1 to 2. Those are the values of t that will be our bounds of integration. So we'll have 1 to 2. And then we're going to have f of t, which is 1/3 t cubed. So I'll write that in. We'll have 1/3 times t cubed. And then that is multiplied by the square root of dx dt squared plus dy dt squared. So we'll have t squared squared plus 1 squared. All right, so we'll have t squared squared plus 1 squared. And then don't forget dt. Okay, and so now we have set up our integral that represents the area of our surface of revolution. Now all we have to do is simplify it and then solve it. Okay, and so the first thing that we can do to simplify this integral is pull this constant multiple of 1/3 out to the front of the integral, right? We don't need to have that inside the integral. We can pull it out front. So we'll have 2 pi times 1/3. That will be 2 pi divided by 3. So this is equal to 2 pi divided by 3 times the integral from 1 to 2 of t cubed times the square root of t squared squared plus 1 squared. Now t squared squared will be t to the 4th power, right? We will multiply these exponents. Whenever you have a value raised to an exponent raised to an exponent, you simplify by multiplying the exponents. So we'll have t to the power of 4, and then we'll add that to 1 squared, which of course is just 1. All right, and then don't forget dt. But now we have fully simplified our integral. Now all that's left to do is determine how to solve it. And so in this case, I see that we have a composite function, right? We have a function within another function. We have the square root of t to the 4th power plus 1. And whenever you have a composite function, you should first try to see if you can use u substitution. It's not always going to work, but there are many cases where it will work. Typically, you want to set the inside function of your composite function equal to u. And so in this case, the outside function is the square root function, and the inside function is t to the 4th power plus 1. And so if we're going to set u equal to that inside function, we need to be sure that the derivative of that is also within the integral. Otherwise, u substitution is not going to work. And so if we were to take the derivative of t to the 4th power, that would result in a function where we'd have t to the 3rd power, right? Because if we use the power rule for derivatives, we have to subtract 1 from this exponent, and so this would become t cubed instead of t to the 4th power. And if you look on the outside of this function, we have t cubed right here. We have a function and its derivative. So u substitution should work pretty nicely here. All right, so if we let u equal t to the 4th power plus 1, the derivative of that du dt will be equal to 4t cubed, right? We multiply the exponent down and then subtract 1 from it. So we have 4 times t to the 3rd power, or 4t cubed, and then the derivative of 1 is 0 because 1 is a constant. All right, and then if we multiply both sides by dt, we can solve for du. Du will be equal to 4t cubed dt. And now whatever du is equal to, we want to be able to find that within our integral. That way we could rewrite the integral in terms of u. And in this case, I don't see 4t cubed dt. I just see t cubed and dt. I don't see that 4. So let's divide both sides by 4, and then we'll have a term of du that is equal to something in terms of t that we can find in our integral and be able to replace it to complete our u substitution. And so if we do that, we'll have du divided by 4 is equal to t cubed dt. Okay, so now we can replace t to the 4th power plus 1 with u, and t cubed dt with du divided by 4. So we will have that this is equal to 2 pi divided by 3 times the integral from t equals 1 to t equals 2 of the square root of u times du divided by 4. Okay, so we replace t to the 4th power plus 1 with u, because that's what we set it equal to, and we replace t cubed dt with du divided by 4, because that is what that is equal to. All right, but this integral is not entirely in terms of u because our bounds of integration are still values of t, right? That's why I wrote t equals 1 and t equals 2, so that we don't forget that these bounds are values of t, not u, but we can change them to be values of u by plugging each of those values into what we set u equal to. So in t equals 2, u will be equal to 2 to the 4th power plus 1, and 2 to the 4th power is 16, so you have 16 plus 1, that will be 17. So our upper bound, instead of t equals 2, that will become u equals 17. So we'll write u equals 17. Then for the lower bound, when t equals 1, u will be equal to 1 to the power of 4 plus 1, and 1 to the 4th power is just 1, so you have 1 plus 1, so u is equal to 2. That will be the lower bound. So I'll replace t equals 1 with u equals 2. All right, so now our integral is entirely in terms of u. We don't have to convert back into terms of t. We can just integrate this expression and then evaluate at our bounds of integration in terms of u. All right, and so now our next step is to simplify this integral a little bit, and then we can use one of our integration rules to solve it. All right, and so the first thing that we can do to simplify this is pull this 1/4 out to the front of the integral. So we'll have 2 pi divided by 3 times 1/4. And so we'll just end up multiplying the denominators of 3 and 4 to get 12. So this is equal to 2 pi divided by 12 times the integral from 2 to 17 of the square root of u. But in order to more easily see how to integrate that using the power rule for integration, I'm going to write it like this. We'll have u to the 1/2 power. That is the same as the square root of u, right? Taking a value to the 1/2 power is the same as taking the square root of that value. And then we're multiplying by du, not du divided by 4 because we pulled out that 1/4 to the front of the integral. Okay, and so now we can solve this integral. We can integrate u to the 1/2 power using the power rule of integration. And so this will be equal to 2 pi divided by 12, but we can reduce that to be pi divided by 6, right? Both 2 pi and 12 are divisible by 2. So if we reduce them by a factor of 2, we'll have pi divided by 6. So we'll have pi divided by 6 times the integral of u to the 1/2 power. We'll add 1 to the exponent and then divide by that new exponent. And 1/2 plus 1 is 3/2. So we'll have u to the 3/2 power divided by 3/2. And that is evaluated from 2 to 17. Okay, now if we continue our work over here, this will be equal to pi divided by 6 times this expression, u to the 3/2 power divided by 3/2. But remember that dividing by a fraction is the same as multiplying by the reciprocal of that fraction. So instead of dividing by 3/2, we can multiply by 2/3. So we'll have 2/3 times u to the 3/2 power, evaluated from 2 to 17. Okay, and now we can pull this 2/3 to the outside. We don't need to include that with u to the 3/2 power. So we'll have 2 times pi and 3 times 6. That will give us 2 pi divided by 18. And then that will be multiplied by u to the 3/2 power, evaluated from 2 to 17. All right, so now we can evaluate u to the 3/2 power at 17 and subtract the evaluation at 2. So this will be equal to 2 pi divided by 18, but that can be reduced by a factor of 2 in the numerator and denominator, right? We have 2 pi divided by 18, 2 pi divided by 2 is pi, and 18 divided by 2 is 9. So this is pi divided by 9, and that will be multiplied by 17 to the 3/2 power minus 2 to the 3/2 power. All right, and so that right there is going to be our final answer. There's actually no way for us to make this solution any simpler. It's a pretty ugly answer, right? Pi divided by 9 times 17 to the 3/2 power minus 2 to the 3/2 power. Both of those values are in their simplest form. We can't manipulate them in any way to look nicer. And so this is our final answer. That would be the exact answer, but you don't really have an idea of what that area actually is. So if you plug this into your calculator, you can get an approximate value that the area of our surface of revolution is approximately equal to 23.4797 and some more decimals. All right, so either of those answers is fine, but you should probably include the exact answer somewhere within your work. All right, but either way, both of these answers represent the area of the surface of revolution formed by revolving the curve represented by these parametric equations from t equals 1 to t equals 2 around the y-axis. Okay, and so that's it for this example, but let's take a look at one more final example for this video. All right, so here's our last example. We want to find the area of the surface formed by revolving the curve represented by the parametric equations around the x-axis. And this time our parametric equations are x equals cosine squared t and y equals cosine t. And then the curve represented by these parametric equations, we're only going to look at the section of it from t equals 0 to t equals pi divided by 2, and that is what's going to be revolved around the x-axis to form a surface of revolution. All right, now since we're working with parametric equations and we're revolving around the x-axis, we will use the following formula to calculate the area of this surface of revolution. We used this formula in our first example. The surface area is equal to 2 pi times the integral from t sub 1 to t sub 2 of g of t, which is what y is equal to from our parametric equations, times the square root of dx dt squared plus dy dt squared dt. All right, and so let's get right into this. In order to set up this integral, we need dx dt and dy dt. So let's take the derivative of each of our parametric equations. And so dx dt is equal to the derivative of cosine squared t. Now this is a composite function. It may not look like it initially, but we could rewrite it. Instead of being cosine squared t, we could have cosine t squared. That would be the same thing. And now you can see that we have a composite function that requires the use of the chain rule. So we're going to need to take the derivative of the outside function first, and then multiply by the derivative of the inside function. In this case, our outside function is the quantity squared, and the inside function is cosine t. So let's take the derivative of the outside function. We will need to use the power rule for derivatives. We'll multiply 2 down and subtract 1 from the exponent and keep that same inside function. And so we'll have 2 times cosine t to the first power times the derivative of that inside function, which is cosine t. And the derivative of cosine is negative sine, so we'll multiply by negative sine t. All right, now if we simplify, cosine t to the first power is just cosine t, and then we're multiplying that by negative sine t, and so I'll just move that negative out front, so dx dt will be equal to negative 2 times cosine t times sine t. All right, so that's dx dt. Now let's find dy dt. That will be equal to the derivative of y, which is cosine t, and the derivative of cosine is negative sine, so we'll have negative sine t. All right, so now we have dx dt and dy dt, so we're ready to set up our integral. But don't forget that we also need g of t, which is just what y is equal to. And so I'll write that down. G of t is equal to cosine t. So now let's set up our integral here. Let's use this formula in order to calculate the area of this surface of revolution. We'll have that s is equal to 2 pi times the integral from t sub 1 to t sub 2, which in this case will be from 0 to pi divided by 2. So we'll have a lower bound of 0 and an upper bound of pi divided by 2. And then inside the integral, we have g of t, which is cosine t. So we'll have cosine t, and multiply that by the square root of dx dt squared plus dy dt squared. And so dx dt is negative 2 cosine t sine t. So that will look like this. We will have negative 2 times cosine t times sine t, and that will be squared. And then we'll add that to dy dt squared, which will be negative sine t squared. All right, and then don't forget dt. Okay, and so now we have set up our integral that represents the area of our surface of revolution. Now all we have to do is simplify the integral and then solve it. And so the first thing that we can simplify in this integral are the contents of this square root. We can square each of these quantities. And so we're going to square each of these parts of this quantity. We're going to square negative 2, we're going to square cosine t, and square sine t, and then we're also going to square negative sine t. All right, so if we do all that, this will be equal to 2 pi times the integral from 0 to pi divided by 2 of cosine t times the square root of negative 2 squared, which is 4, times cosine t squared, that will be cosine squared t, times sine t squared, which will be sine squared t. And then we'll add that to negative sine t squared, which is just going to be positive sine squared t, right? When you square a negative value, it becomes positive. So we're just going to have positive sine squared t, and then dt. All right, and so now to simplify further, notice that both of these terms contain sine squared t in them. What you want to do whenever you see a common factor in both of your terms underneath this square root is pull that common factor out. So we're going to pull sine squared t out of both of these terms, and that's going to help us simplify the integral. So this will be equal to 2 pi times the integral from 0 to pi divided by 2 of cosine t times the square root of sine squared t times 4 times cosine squared t plus 1, and then dt, right? So we pulled sine squared t out of both of these terms. So if we pull it out of this first term, all we're left with is 4 cosine squared t right here. And then if we pull it out of this term, well, sine squared t is the only thing in this term, so we're left over with 1. Okay, so now we have the square root of sine squared t times that quantity, 4 times cosine squared t plus 1. And now what we can do is take the square root of both of these parts. And the square root of sine squared t is just going to be sine t. And so what we'll have is that this is equal to 2 pi times the integral from 0 to pi divided by 2 of cosine t times sine t times the square root of 4 times cosine squared t plus 1 dt. Okay, so we took the square root of both parts. The square root of sine squared t is just sine t, and then the square root of this quantity is right here. And so now at this point, our integral is in its simplest form. There's really nothing for us to simplify any further. So let's see if we can use any of our known integration techniques in order to solve this integral. And so the first thing that I always try to do is see if I can use u substitution, especially in this case, since we have a composite function, right? We have a square root of another function. We have an outside function and an inside function. And typically that's a good sign that you want to use u substitution. You typically want to set the inside function equal to u, but that's only going to work if the derivative of u is also found within your integral. And so the question is, if we set u equal to 4 times cosine squared t plus 1, would the derivative of that function be found in this integral? In other words, is the derivative of this inside function close to cosine t times sine t? And I say close because we're not really worried about any constant multiples being off. We're just worried about, is the derivative of this function going to include cosine t and sine t? And if you remember when we found dx dt, when we originally set up our integral, when we took the derivative of x with respect to t, x was equal to cosine squared t, which is very similar to what we have right here. The derivative of cosine squared t did involve cosine and sine. All right, and so let me show you what's going to happen here. Let's set u equal to this inside function, and u substitution is going to work out very nicely. If u is equal to 4 times cosine squared t plus 1, then du dt will be equal to the derivative of those two terms. Now the derivative of 1 is 0, so we don't need to worry about that, but the derivative of 4 times cosine squared t is going to be pretty interesting. Because remember, we can rewrite cosine squared t to be cosine squared. So let's just do that. We'll have cosine t squared. And so if we use the chain rule here, the derivative of the outside function will give us 4 times 2 times cosine t, right? We multiply the exponent down. So we have 4 times 2, and then you subtract 1 from the exponent. So you just have cosine t to the first power, which is cosine t. But then we need to multiply by the derivative of the inside function. That's the second part of the chain rule. And the derivative of cosine is negative sine. So we'll have negative sine t. And then if we simplify this, 4 times 2 is 8, and then this negative will come out front to make it negative 8. Du dt will be equal to negative 8 times cosine t times sine t. And ignoring this negative 8, cosine t sine t can be found within our integral right here. We have a function and its derivative. So u substitution is going to work very nicely for this integral. What seemed to be a very complicated integral is now going to become very simple and easy to integrate. All we have to do is solve for du, and then make sure whatever it is equal to can be found within our integral. And so hopefully you can already see what's going to happen here, that negative 8 is not within this integral, so we're going to need to divide both sides by negative 8. But let's not get too far ahead of ourselves. Let's first start by solving for du. Let's multiply both sides of this equation by dt. We'll have du is equal to negative 8 times cosine t times sine t, and then we have dt. And now we can divide both sides by negative 8 so that we have a term of du that is equal to something that we can find in our integral. So du divided by negative 8 will be equal to cosine t times sine t dt. Okay, so now let's use u substitution. Let's rewrite our integral in terms of u. So this will be equal to 2 pi times the integral from t equals 0 to t equals pi divided by 2 of the square root of u times du divided by negative 8. That is all this integral becomes. We replaced 4 cosine squared t plus 1 with u, because that's what we set it equal to, and we replaced cosine t times sine t times dt with du divided by negative 8, because that is what that is equal to. All right, and so now we have an integral that is much easier to integrate. We can see how we can integrate the square root of u, but before we do that, we should rewrite our bounds of integration in terms of u. That way our whole integral will be in terms of u. And so we can do that by plugging in these values of t into the equation for what we set u equal to. And so if we start with our upper bound of t equals pi divided by 2, if we plug that into this equation, u will be equal to 4 times cosine of pi divided by 2 squared plus 1. Now cosine of pi divided by 2 is 0, so we'll have 0 squared, which is 0, times 4, which is 0, plus 1. So that upper bound is just going to be 1. Okay, so we'll replace t equals pi divided by 2 with u equals 1. So we'll have u equals 1. Then for the lower bound, we have t equals 0. If we plug that into this equation, we'll have u equals 4 times cosine of 0 squared plus 1. And cosine of 0 is 1. So we have 1 squared, which is 1, times 4, which is 4, plus 1, which is 5. So u equals 5 will be our new lower bound. So we'll replace t equals 0 with u equals 5. Okay, and so now our integral is entirely in terms of u. We don't have to convert back into terms of t. We can just integrate this in terms of u and evaluate at our bounds of integration in terms of u. Okay? And so before we solve this integral, let's simplify it a little bit. We can make it nicer before we try to solve it. First thing I'm going to do is pull this negative 1/8 out to the front of the integral. So this will be equal to 2 pi times negative 1/8. But 2 divided by 8 will become 1/4. So really we'll just have negative pi divided by 4. So I'll erase this. 2 pi times negative 1/8 will be negative pi divided by 4. And so that will be multiplied by the integral from 5 to 1 of u to the 1/2 power times du. All right, so I just rewrote the square root of u to be u to the 1/2 power, just so it's easier to see how we can integrate that term by using the power rule of integration. But now before we do that, I want to make our evaluation process go a lot nicer, because if you look at our bounds of integration, notice that the lower bound is bigger than the upper bound. That's a little unusual to see. That's just a result of the u substitution process. But what we can do is actually flip those bounds of integration and negate our integral. That's one of the properties of definite integrals. You are allowed to swap the bounds of integration as long as you then remember to add a negative sign to your integral. And so in this case, that would actually remove this negative sign right here, because 2 negative signs will cancel out to become positive. So this actually will be equal to positive pi divided by 4 times the integral from 1 to 5 of u to the 1/2 power du. Okay, so all we did was swap our bounds of integration. Instead of integrating from 5 to 1, we are now integrating from 1 to 5. And in order to do that, we had to negate the integral, so negative pi divided by 4 became positive pi divided by 4. Okay, so now we can integrate, and let's do that over here. This will be equal to pi divided by 4 times u to the 3/2 power divided by 3/2 evaluated from 1 to 5. Right, if we use the power rule for integration, we add 1 to that exponent and divide by that new exponent, and 1/2 plus 1 is 3/2, and so we divide by 3/2. Okay, now dividing by a fraction is the same as multiplying by the reciprocal of that fraction, so instead of dividing by 3/2, we can multiply by 2/3. So this will be equal to pi divided by 4 times 2/3 times u to the 3/2 power evaluated from 1 to 5. And then the next thing that we can do is pull this 2/3 to the outside. We can multiply 2/3 by pi divided by 4. And so this will be equal to 2 pi divided by 12, right? 2 times pi is 2 pi, and 4 times 3 is 12. And that will be multiplied by u to the 3/2 power evaluated from 1 to 5. All right, and so now this will be equal to pi divided by 6, right? 2 pi and 12 can both be reduced by a factor of 2. So 2 pi becomes pi, and 12 becomes 6, times 5 to the 3/2 power minus 1 to the 3/2 power, right? We evaluate this expression at 5 and subtract the evaluation at 1. So we have 5 to the 3/2 power minus 1 to the 3/2 power, but 1 to the 3/2 power is just 1, right? 1 to the power of anything is 1, and so this is just going to be 5 to the 3/2 power minus 1. And this right here is the exact answer for the area of the surface of revolution in this problem. However, it is an ugly answer. It's not very clear what the value of our area is. At least it's hard for us to visualize that area. And so if you want to, you can plug it into your calculator to get an approximate value, and that will tell you that this is approximately equal to 5.3304 and some more decimals. So that's the approximate value of the area. But this answer right here would be the exact area, which is typically what you want to solve for in these problems. Okay, so both of these answers would be correct. They both represent the area of the surface of revolution formed by revolving the curve represented by these parametric equations between these two values of t around the x-axis. Okay, and so with that, this was the last example for this video. So if you have any questions, feel free to leave those in the comments. But if you don't have any questions, this is all I had for now. So I will see you next time.